Alright, so in this second lecture, we will do some analysis of the Hohmann transfer that we studied in the previous lecture. Uh, what we will do here is essentially some graphical analysis. Okay, so we'll try to get some trends and see how the Hohmann transfer looks like as we try to transfer the spacecraft from a fixed initial orbit to different final orbits. Alright. So to start this, if you look at figure 2 of part 2 of the notes on orbital maneuvers, we'll try to look at how the trends look over there. So figure 2 in the notes looks something like this. On the x-axis, I have the ratio chi, which is the ratio of the radius of the final orbit to the radius of the initial orbit, and on the y-axis I have delta V that is needed. All right. So and the unit here is kilometers per second. All right. So we will plot delta V1, delta V2, and the total delta V, all three separately. Okay. So let us look at delta V1 first. So 20, 60, 80, and so on. And so you have the actual numbers in the graph and the notes. I'm going to show you the trend here. So it increases. Well, delta V1 is monotonic and increases all the way, but then it flattens out and shows an asymptotic behavior. Okay, so it flattens out. All right, this one is delta V1. So on the y-axis I have this is 3. Okay, that's delta V1. All right, delta V2 shows a very different behavior. It increases initially, just like delta V1, but then it starts to fall down. Okay, so this is delta V2. You remember delta V2 is the circularization maneuver, and we have the green one is delta V1. Okay, and when we add these two, we get the total delta V. So since this one is becoming flat and this one is actually falling down all the way to 0, the total delta V will show a similar trend. Add these two. Okay, this is delta V total. All right. So what is going on in these curves? Let's try to analyze the behavior here. So as you can see, delta V2 rises initially and then it starts decreasing as the ratio of the final to the initial increases. Okay, the question is why? Well, you can explain this two ways. One is if you just look at the expression for delta V2, and the expression for delta V2 is, look back in your notes, this is equation 12 in the notes, and you have Vi. Oh, by the way, the initial orbit is assumed to be circular, obviously, of altitude 400 kilometers. So initial is 400 kilometer altitude orbit. Okay, so if you remember, there are only two parameters that we had in the entire analysis of Hohmann transfers. The first parameter was Vi, which is the velocity in the initial orbit, and chi, which I have here. So the assumption for Vi is that Vi corresponds to the circular speed at 400 kilometers altitude. Okay, so here's Vi, 1 over square root chi minus 2 chi plus 1. Okay, so as chi increases, here's this function. Basically, this black dotted line is this function plotted as a function of chi, right? And what happens is that as chi increases to infinity, this curve dies out to 0. Okay, so if I use the limit chi goes to infinity, chi goes to infinity, this value is nothing but 0. Okay, so what we are saying is that if my final orbit RF lies at infinity, then there is no delta V needed for circularization. Okay, delta V circularization is 0. Now that may sound a little perplexing, but it makes perfect sense. Okay, and the way to look at it is if we draw the picture of the Hohmann transfer. So here's my initial orbit, the focus F, initial orbit, and the final orbit. Okay, and here's my transfer ellipse. Now what we are saying is, as the ratio chi increases, right, delta V2 takes place here, right? So what we are saying is that as the ratio, meaning that the chi ratio increases, which means that this outer orbit becomes bigger and bigger, eventually becoming a circle of infinite radius. Okay, delta V2 goes to 0. Now why is that? If this outer orbit is at infinity, then the transfer ellipse must also be so large that it reaches all the way to infinity. Okay, so it's not really a transfer ellipse, right? It is a transfer parabola, because this transfer orbit must reach all the way to infinity, right? A closed orbit will never go to infinity. So we are operating in the boundary, right? As this outer orbit goes to infinity, this transfer ellipse essentially becomes a transfer parabola, right? So the velocity on the transfer parabola at this point, now this point lies at infinity, right? So the velocity on the transfer parabola at that point is going to be 0, because the transfer parabola has 0 excess velocity, right? At infinity the speed becomes 0. And also the speed on this final orbit is going to be also 0, right? Because if you remember, the speed on a circular orbit is square root mu over r. Now this r, which is rf, is infinity. So infinity in the denominator means that the speed on that, it's almost a fictitious orbit at infinity, is 0, which means that there is absolutely no difference in the speed of the spacecraft on the transfer ellipse parabola and the final orbit. Therefore, the delta V, which is the difference between the speeds on those two orbits, is also 0, right? So it is kind of a limiting case of the Hohmann transfer. What we are really looking at is the escape velocity at this point. That's what we need, right? If we impart enough speed here so that the spacecraft enters a parabola, which means it escapes, then it will go all the way to infinity. At infinity, it will reach 0 speed, and the final orbit also has 0 speed. All right, so basically we get that delta V2, which is the difference between the speeds of the final orbit and the transfer ellipse, is 0. and therefore we see that no effort is needed as the final orbit reaches infinity. Okay, so that explains the behavior of delta V2. All right. Now, let us look at what happens to delta V1. So, if you recall that the expression for delta V1, which was equation number, I don't remember what equation number it was, but basically it is Vi 2 chi plus 1 minus 1. Okay, that is delta V1, which is my green curve here. Now as I take the limit, chi goes to infinity, limit chi goes to infinity, then these two chi's will basically cancel out and I will get Vi square root 2 minus 1. Okay, now this looks familiar because when we did the single impulse maneuvers, this delta V was nothing but delta V escape. Okay, so let me just write a delta V escape, which again makes perfect sense because what we are saying is that if chi is infinity, which means that my final orbit is at infinity, this transfer ellipse must be able to reach all the way to infinity, which means again that it's not really an ellipse, it's a parabola. So the delta V1 needed here to go from the initial orbit to the transfer orbit translates to delta V required to go from initial orbit to the escape parabola, and therefore we get delta V escape. Okay, and so this green curve flattens out and therefore we get the limiting value. This limiting value is delta V escape. Okay, so as chi goes to infinity, delta V1 goes to delta V escape. And finally, the total delta V, which is the sum of delta V1 and delta V2, also flattens out at delta V escape because delta V2 goes to 0. So delta Vt at infinity is delta V1. Okay, but it reaches delta V escape from the top, not from the bottom, like delta V1 does. Okay, so this makes perfect sense and it gives you a nice feel for how the Hohmann transfer would look like as the final orbit expands and reaches all the way up to infinity. The next plot is pretty straightforward, which is figure 3 in your notes. And it shows the transfer time for the Hohmann transfer as the ratio of the initial and final orbits increases. Okay, this is the transfer time, and this is this is a easy graph to plot. That's the trend, and you have T, 40, so on. So here you have hours. Okay, so basically what we are saying is as the outer orbit goes further and further away, the amount of time needed to reach there will increase. Okay, and this is not an exponential increase. Okay, it's very easy to figure out what the rate of growth is. Remember that the transfer time depends only on is equal to half the period of the transfer ellipse. The period of the transfer ellipse depends on its semi-major axis from Kepler's third law. The semi-major axis depends on, for a fixed initial radius, it depends on the radius of the final orbit. So T is equal to pt over 2, which is proportional to at cube. Okay, and so this is goes as rf cube. So, right, because at is ri plus rf over 2. So this is a polynomial type of growth. Okay, so that's fine. Now, the last figure that we have is very interesting. Okay, this is figure 4 in the notes. And what it does, this picture compares the delta V's that are needed for typical Hohmann transfers with delta V's that are needed for plane changes. Okay, so let me draw the picture first. On the x-axis, I have delta V over Vi, so I have delta V as a ratio. So essentially what I'm doing is I'm removing the effect of Vi. Okay, alright, so that's my independent variable. Then on the y-axis, on the left, I have chi. So given a certain delta V, okay, again I'm going to assume that the initial orbit is, this corresponds to 400 kilometers altitude. That's my initial orbit. Okay, so for a given delta V, what is the final orbit that I can reach? Okay, that's my y-axis, because chi is rf over ri. Since Vi is given is 400 kilometers, this is radius of Earth plus 400 kilometers. Okay, this is fixed. What I'm looking for is what is the RF I can reach given a value of delta V. Okay, so this plot obviously begins at 1, not at 0, right? Because for delta V equal to 0, nothing happens. So chi is equal to 1, meaning RF is equal to Ri. So I start at 1 and initially goes like that. Okay. So this is nothing but the previous figure, the delta V figure inverted, right? I had delta V on the y-axis and chi on the x-axis. I've reversed that here. Okay. Now I'm also plotting on another y-axis on the right side plane change, delta I in degrees. So the point here is, given a delta V, how much plane change I can achieve, right? When my initial orbit is 400 kilometers circular. So this plot, now when delta V is 0, delta I is 0, right? No plane change will happen. So this plot starts at 0. There's a different color here. Starts at 0, and you remember that delta V was 2 times Vi sine delta I over 2. So this is a sine type of curve. And plot it, goes like that. Okay, so here's the meeting point, and this is about 28 degrees. Okay, on the delta I side of things, and the corresponding chi over here is about 95 or so. So what we are saying is that if I give you the delta V that is sufficient to achieve a 28 degrees plane change, and use that delta V not for a plane change but for a Hohmann transfer, then I can reach a final orbit that is 95 times the radius of the initial orbit, right? So essentially what we are saying is that a 28-degree plane change for a 400-kilometer initial orbit is equivalent in delta V terms to a Hohmann transfer between the initial orbit and a final orbit 95 times larger than the initial orbit. So that gives you, puts things in perspective, that plane changes are so expensive, right? And for that, because for that value, I can achieve such a big transfer to a final orbit that's so much bigger than the initial orbit. Okay, so there is something even more interesting to note here, is that what we saw two figures ago, that the total delta V actually starts to decrease after a certain point, right? As chi goes to infinity, delta V2 goes to 0, and delta V1 goes to delta V escape, which also equals delta V total. So the Hohmann transfer, which very non-intuitively becomes easier, right? As the orbit, the final orbit, becomes larger than a threshold. Okay, here's the threshold right here. You see that delta V is increasing, but then after a point, this is the threshold, chi. Delta V starts to go down. This is highly non-intuitive, right? Because what we are saying is that to achieve a bigger orbit, I need a lesser delta V. Okay? So I want you to think about that a little bit, okay, and try and explain that. The basic idea is that delta V2 goes to 0, okay? As the orbit size becomes bigger and bigger, the transfer ellipse gets closer and closer to the final orbit in terms of the velocities at the point where delta V2 takes place. Okay, therefore the second effort that is needed, the second impulse that is needed, goes to 0, and that leads to a decrease in the total delta V. Okay, all right, so next up we will look at a very important practical application that involves both Hohmann transfers and plane change maneuvers. And what we have in mind is basically to place a spacecraft in a geostationary orbit. Okay, starting from launch, we need to take the spacecraft all the way up to GEO. Now GEO is the geostationary equatorial orbit, which means it's an equatorial orbit, which means that the inclination of this orbit is 0. Okay, so here's our objective. Place a spacecraft in GEO starting from the Kennedy Space Center. Okay. Now we all know that geostationary orbits are extremely important because that's where our communication satellites are placed. So this is a very important application. Now, right now we are in part 3 of the notes on orbital maneuvers, and as you will see in those notes, that there are 3 main steps that are involved in achieving this objective. The first step is starting from launch. So the spacecraft, the rocket has already been launched, and the launch takes place in an eastward direction. So from the launch arc, we transfer the spacecraft into the first orbit, which is known as a parking orbit. Okay, so we will first try to get the spacecraft in what is known as a parking orbit and see this pictorially. I'll try to draw this as best as I can. You can find the color slide on Sakai, and also there's a picture in the notes. So here's the Earth, okay, and very important, here's the equator, okay. The plane of the equatorial is the equatorial plane, and that plane is coincident with the plane of GEO. Now, this is 0 latitude, right? Equator is. The Kennedy Space Center is around 28 degrees latitude north. So I'm going to say that that dot over there is the Kennedy Space Center. Okay. So the launch takes place in an eastward direction, and this solid arc is the launch arc. Okay. That's how the launch takes place. Now at the end of the launch arc is the point which is known as an insertion point. Okay? And at the insertion point, the spacecraft is transferred into what is known as the parking orbit. So I'm going to try to draw this again. So this dotted blue line is the parking orbit. Okay, as you can see, the parking orbit is not equatorial, it has an inclination. Alright, so we need to, at some point, we'll need to do a plane change because our target is to reach equatorial orbit, but right now we are not in the equatorial plane. So this parking orbit I'm going to call O1. Okay, and O1 is parking orbit, and it is a circular orbit. Typically it has a radius or altitude of 300 kilometers. Okay, that's a very typical value. Alright, now before I talk any further about what the next steps are, I'm going to show you the overall picture, okay, what happens. So there are many ways in which you can take the spacecraft from the parking orbit to the final geostationary equatorial orbit. So the first method I will show you first is we go from O1 to another orbit, O2, shown here in green. Okay, call this O2. So what is O2? O2 is an intermediate orbit and its radius, it is also circular. Okay, we are dealing with only circular orbits here. This intermediate orbit O2 has the same radius as the parking orbit. Okay, so it has the same altitude as the parking orbit, but the difference between O2 and O1 is that O2 has zero inclination. Okay, so the transfer between O1 and O2 involves a pure plane change maneuver. That's our second step. Okay, the first step was to place the spacecraft in O1. The second step is to go from O1 to O2 via a plane change maneuver. Alright, then the final step is to perform a Hohmann transfer. A Hohmann transfer, if you remember, takes place between two coplanar circular orbits. Okay, so O2 is coplanar with GEO because O2 is equatorial, it has zero inclination, so is GEO, alright, and they are both circular. So I'm going to draw in black now. black orbit O3 is geo, and we know that its radius is about 42,000 kilometers, right? Let me get the actual number. So radius 42,164 km. That's the radius, not the altitude. Okay, and it has 0-degree inclination. So how would we go from O2 to O3? It's a simple Hohmann transfer, right? To Hohmann transfer to go from O2 to O3. Alright, this is one method of achieving this objective, right? There are many other methods, at least two of which I have described in the notes. Two other methods as well that I have described in the notes. Alright, so we'll go now step by step and look at how this process unfolds. Okay. Now, the first step was to place the spacecraft in O1, which is the parking orbit. Okay. Get rid of this. All right. So, first step is the parking orbit. And we know that it is 300 kilometers altitude, and its inclination is not 0, right? Because it is launched from a launch site which is not on the equator. Okay, because of the fact that the launch site has a non-zero latitude, the inclination of the resulting orbit, the parking orbit, will not be 0. Okay. Now, it turns out that the inclination of the parking orbit, I, depends on two things. Okay. The first is phi, where phi is the latitude of the launch site, and it also depends on another angle, A, which is the so-called azimuth angle. Okay, phi is the latitude of launch site, and A is the azimuth at insertion. Remember the insertion point. It is the meeting point between the launch arc and the parking orbit. Okay. Now the azimuth is the direction of flight of the vehicle, okay, at the point of insertion, and this direction of flight is measured clockwise from a direction that points north. Okay, so if this is my local north and the insertion takes place in an eastward direction, which is how it is done, I measure clockwise, right? That angle is 90 degrees as the azimuth. Okay, so we get that the inclination of the parking orbit is equal to cos phi sine 90 degrees. This is 1. This is for an eastward insertion, which means that I is equal to phi. Okay, so the phi is nothing but the phi of the KSC, which is a launch site, which is approximately 28.6 degrees. So this is what we are working with. Our parking orbit has 300 kilometers altitude, and an inclination of about 29 degrees. Okay. Now our final destination is O3, which is geo. And like I said earlier, there are many different ways of getting there. Okay. So the first way, the picture that I drew a little while ago, was to go from O1 to O2, which is an intermediate orbit, which is the same as O1 except the fact that it has zero inclination. And step 3 is to go from O2 to the final geo. Alright, so let me lay out the first method. Method A. Okay, here's step 2 of method A. Step 1 is to establish the parking orbit. Okay, so the step 2 of method A is to perform plane change. To go from O1 to O2. Okay. Now, we don't want to change the radius of the parking orbit. We simply want a pure inclination change. So from our study of single impulse maneuvers, remember that a pure inclination change can be achieved by a rotation of the velocity vector, and that rotation must take place at either the ascending node or the descending node. Okay, so if I draw that picture again, here's the Earth and the equator. Here's my parking orbit. Okay, here's the equator. So here's the line of the nodes. Right, those 2 points are my ascending and descending nodes. So at one of those 2 points, I need to rotate the direction of the velocity vector so that my final orbit, which is O2, can be achieved. Okay. All right. So that's the second step. The third step, step 3 of method A, is to go from O2 to O3, O1, O2. Now to go from O2 to O3 by performing a Hohmann transfer. Perform a Hohmann transfer to go from O2, which is my intermediate orbit, to O3, which is geo. This Hohmann transfer is valid, or it works, because O3 is coplanar with O2, right? They're both equatorial orbits. All right. This is method A. There is another simple method that can be used. Okay, so let me describe that. Method B. Step 1 of method B is the same as the step 1 of method A, which is to first establish the parking orbit. Okay, the parking orbit is the same for both methods, so O1 is the same. In step 2 of method B, again, we move the spacecraft into an intermediate orbit O2, but this O2 is different from O2 of method A. Okay, what we do here first is perform the Hohmann transfer. Hohmann transfer to go from O1, which is parking, to O2. What is this O2? This O2 cannot be the same as the O2 in the previous method, right? Because in the previous method, O1 and O2 had different inclinations, meaning that they were not coplanar, right? So if I am going to do a Hohmann transfer, the resulting orbit O2 must have the same inclination as O1. So what this O2 is going to look like is that it will also be circular with the inclination. What should be the inclination of O2? The inclination of O2 will be the same as the inclination of O1, right? Because a Hohmann transfer initial and final orbits have the same plane. So inclination is going to be the same as that of O1, but O2 is going to be bigger than O1, right? That's what Hohmann transfer does. It takes you from a smaller orbit to a bigger orbit, or vice versa. I mean, you can go either way. So the radius of O2, here we are going to a bigger orbit from O1 to O2, and radius of O2 is equal to the radius of GO, which is 42,164 kilometers. Okay, so what are we doing basically? What is the difference between method A and method B? In method A, we first did the plane change. Okay, we ended up in an equatorial orbit, and then we expanded it out to reach out to the GO. Here what we are doing is first we are expanding out the parking orbit to reach, as far as the GO first, and then in step 3 of method B, we will perform a plane change to go from this new intermediate orbit. To distinguish between the two methods, let me put a prime in there. Okay, so this is O2 prime. Go from O2 prime to O3, but O3 is GO, right? So note that O2 prime and O3 have the same radius, right? They are the same size. The only difference between O2 prime and O3 is that they have a different inclination. So at the descending or ascending node of O2 prime, I'm going to perform a plane change maneuver of this magnitude, 28.6 degrees, to make the orbit equatorial. Okay. The question is, why are these two methods different? Question is, how are these two methods different, first of all? Right? In the first method, we first do the plane change and then do the Hohmann transfer. Here, we are doing the Hohmann transfer first and then the plane change. Okay. So here's the big picture. The Hohmann transfer delta V is the same in both methods A and B. Why is that? Remember that the Hohmann transfer depends on only two things, right? The Hohmann transfer, the delta V of Hohmann transfer, I will draw the picture for method B in a little bit. But first note that the delta V total of Hohmann transfer is a function of only two things, right? Function of Vi and chi, right? Chi is the ratio of the radii of the initial and final orbits. Vi is the speed in the initial orbit, but Vi in turn is a function of Ri, right? Remember that Vi is equal to square root mu over Ri. Correct? So I can replace this and say that it is this delta V total in Hohmann transfer is a function of Ri and chi. Okay. Now Ri is the same in both methods A and B. Okay. So let me draw two clumsy pictures here. Okay. Here's the Earth, equator. Here's my parking orbit. Here's the intermediate orbit. And here's the final geo. Okay. This is method A. Method B. Here's the Earth, equator, parking orbit. Parking orbit in both these methods is the same. Now, the intermediate orbit looks very different here. Here's the intermediate orbit. Okay, the intermediate orbit O2 prime has the same inclination as the parking orbit, but it is of the same size as the geo. The final orbit again, this is O3, is geo, so that the difference here is 28.6 degrees. Right? So in method A, here's the Hohmann transfer from green to black. Right? From green to black, Ri is the radius of green. Okay. Here, Hohmann transfer is from black to green. Right? Ri is the radius of black, which is the same as the radius of green here. Right? So the Ri is the same in both these methods. Chi depends on Rf. Right? Chi is again the same in both these methods because chi depends on the radius of the geostationary orbit, so that the delta V, what we end up, that the delta V, total delta V for the Hohmann transfer part of both methods is the same for methods A and B. Alright, now delta V plane change is Vi 2 times Vi sine delta I over 2, right? So this is a function, once again, of Vi and delta I. But Vi is a function of Ri just like before. So I'm going to say that delta V plane change is a function of Ri and delta I. Delta I in methods A and B are the same, right? Because here I need a plane change of 28.6 degrees. Here again I need a plane change of 28.6 degrees. The difference is that where the plane change occurs, right? In method in method A, the plane change occurs closer to the Earth. So Ri is small. Ri is small means that Vi is large. Vi is large means delta V is large. Okay. So the only difference between methods A and B is in the delta V that is needed for the plane change, because the plane change occurs at different locations. Even though the magnitude of the plane change is the same, 28.6 degrees, the location is different. So it's going to make a it's gonna make a difference, and it's a pretty significant difference, as we'll soon see, on how much delta V is needed for the plane change. Okay, so I hope that is clear. If not, I'll be in class soon, and Also, you can write an email to me. Um, so let us try and analyze both these different methods and compute the delta V needed to achieve geostationary equatorial orbit. Alright, so we will perform our analysis only for steps 2 and 3 of both these methods. Okay, so method A. Remember the first step, or this, the second step of method A, step 2A, was a plane change maneuver to go from O1, which is parking, to O2, which is intermediate. This has 0 degree inclination. I'm sorry. This has 28.6 degrees inclination. So parking orbit, and this guy has a 0 degree inclination. It's equatorial orbit of the same radius as the parking orbit. Okay, so this is pretty straightforward. The initial speed is the speed on VI. I'm sorry, the speed on O1. So VI is square root mu over RO1. RO1. Right, which is the radius of the parking orbit. Now, the altitude is 300 kilometers. So the radius is radius of Earth plus 300 kilometers, and this turns out to be, this is RE, radius of Earth plus 300 kilometers. So this speed turns out to be 7.7258 kilometers per second. Okay, so delta V, plane change. Now in my notes I have unfortunate notational mix-up. Well, it's not a mix-up. I have just an unfortunate notation. I'm calling this delta V plane change, which is method A, first delta V. I should have actually called it delta VA2 because it's step 2, but it's the first delta V that takes place in step 2. That's why I have A1. So method A, first delta V. This is the plane change delta V. This is, we know, 2VI sine delta I over 2. Okay. We know that delta I magnitude is 28.6 degrees. So delta I is 28.6 degrees. So this turns out to be, using the VI that we have up there, is this huge 3.8165 kilometers per second. Okay. A lot of delta V. Alright. Remember that this delta V A1 takes place at either the ascending node or the descending node of the parking orbit. Alright. We're still in method A. Look at step 3 of method A. This is the Hohmann transfer. So go from O2 to O3. Okay. So remember, there were 3 steps in the Hohmann transfer, so let us go through the process. First step was to design the transfer ellipse. Here, Ri, initial radius, is the radius of O2, which is R park. Remember that O2 and O1 have the same radius. So this is our radius of Earth plus 300 kilometers. And RF, final radius, is RGEO, that's where we want to go, and this is 42164 kilometers. And so from here, the first parameter that we need for the Hohmann transfer is chi, RF over RI. This ratio is 6.3143. Okay, 6.3 times is the expansion that is needed. And therefore our transfer ellipse AT is the mean, the initial and final, stands out to be 24,400 kilometers. And therefore the period from Kepler's third law is equal to 10.55 hours. Okay. Therefore, the total delta V, well, so the steps 2 and 3 of the Hohmann transfer I'm going to combine into the single step. The total delta V for the Hohmann transfer part, step A 2. Okay, step delta V A1 was the first delta V needed. That was the plane change. Delta V A2 is the second delta V needed for method A. This is a combination of two maneuvers. Remember that the Hohmann transfer is a two-impulse maneuver, right? The first impulse takes place at O2, second impulse takes place at O3. Okay, this is the first impulse, the second impulse of Hohmann. And so basically these are steps 2 and 3 of the Hohmann transfer. And so I'm going to get rid of this and write the composite expression back here. Okay. So I have delta V A2 method A, second delta V, is equal to VI. This expression we derived in the previous lecture. 2 chi plus 1 minus 1 plus Vi over chi square root. Okay. Again, this is delta V A21, the first impulse. Here's the second impulse of the Hohmann transfer, A22. Okay. So when I add this up, I get 3.8926 kilometers per second. Okay. All right. So in method A, our conclusion is that the total delta V for method A is delta V first impulse plus first and second impulse of Hohmann. This is plane change. And this adds up to 7.7091 kilometers per second, which is massive. now what I'm going to state next is false, but just go with it for now. The time needed. What is the time needed for this maneuver, this entire maneuver? The plane change maneuver takes no time because it's just an impulse. And the Hohmann transfer is what takes up time. And so T, method A, is T Hohmann transfer, T transfer ellipse over 2, which is what? 5.28 hours. And then I'm going to say quickly that this is incorrect. And why is that? Why do you think that this time needed is incorrect? The reason that this is incorrect is because even though the impulse involved in plane change does not take any time, you have to do some weighting. Okay, because remember that the plane change maneuver must occur at the ascending or descending node. Now once you put the spacecraft in the parking orbit, it is not in the ascending or descending node, right? So you have to wait some time before it gets there. You make the plane change, the impulse itself doesn't take any time, and then instantly at that moment you can transfer to the Hohmann transfer ellipse, right? So there is no waiting time there, but in reality I must say that there's a wait time plus delta t wait for implementing the plane change. Okay, I need to wait until I get to the ascending or descending node. Okay, so that's what is the final number as far as delta V is concerned for method A. Alright, next, keep this in mind, it's about 7.7 kilometers per second. A lot of delta V. Alright, next we will look at method B. Okay. So the second step of method B was to go from O1 to O2 prime. Okay, and remember the O2 prime was a big orbit with the same radius as that of the geostationary orbit, but inclined at the same inclination as O1. Okay, so O1 is 300 kilometers, 28.6 degrees inclination. O2 is I'm going to say 35,000 kilometers approximately. This is the altitude. This is the altitude. Same size as Geo, right? The radius is 42,000. Altitude is 42,000 minus the radius of Earth, which is about 35,000 kilometers and 28.6 degrees. Okay, so here's the Hohmann transfer that is needed. Okay, so we are doing the Hohmann transfer first. So like we did for method A, let us compute the transfer ellipse first. Transfer ellipse, my Ri is R park, which is R01, right? The initial orbit is O1. So the initial radius is R01, which is R park, which is 300 plus RE kilometers, and RF is, this is altitude, RGO, which is 42,164 kilometers. This means that chi, like we argued earlier, is the same as method A, step 3 of method A. Okay, so chi is the same, 6.3143. And so for the transfer ellipse, AT is the mean, everything is the same. Okay, 24,421 kilometers, and the period is 10.55 hours. So it's not a surprise at all that the delta V is going to be the same. Delta V, method B, first delta V is decomposed of two parts, the two parts of the Hohmann transfer, and here's the Hohmann transfer. Okay, this is this and this is that. The two maneuvers in the Hohmann transfer, and so Vi and chi are the same as before in method A. So this part is going to give me the same value of delta V is equal to 3.8926 kilometers per second, and this we found same number we found for method A, but it was the second step of method A, or the second delta V of method A. Okay. All right. To finish out method B, we have step 3 of method B. This is to go from O2 prime to O3, right? This is the radius and inclination that we have reached so far. The same radius, but 0 degrees inclination. Okay. All right. So we remember that delta V plane change method B, second delta V, is 2vi initial speed sine delta I over 2. See, this vi is the speed, the speed on the initial orbit. The initial orbit here is O2 prime, right? O2 prime corresponds to this radius. So vi, I want to say under quotes because this is not the same vi as before, right? Where we were talking about O1. So the initial speed now corresponds to O2 prime is this radius RGO, and that speed is much smaller, 3.0743 kilometers per second, and therefore delta V B2, which is the plane change maneuver, is, put this Vi in here, and delta I is the same, 28.6 degrees, and this turns out to be much less kilometers per second. Okay, and therefore to finish off, total delta V for method B is delta V B1, which is the Hohmann transfer, consists of those two steps, plus delta V B2, which is the plane change right here, and this is 5.4114 kilometers per second. Okay, so as you can see that this delta VB is much less, is less than delta VA, and the reason is that the plane change is less expensive for method B because we are doing the same plane change but for a bigger orbit where the speeds are slower, right? And so since the plane change maneuver is directly proportional to the speed, a slower speed means a lower delta V. And it's quite significant because remember it was around 7.7 something, here it's 5.4, so you have saved 2.3 kilometers per second in delta V just doing this simplistic approach. Okay, alright, that's nice. It appears that method B should be preferred over method A, but like I will show you in the next lecture that there is an even better method. But to finish this part off first, for method B, the time taken is again the time that is involved in the Hohmann transfer, which is the same as method A. This is about 5.28 hours. And again, quickly I will say that this is wrong because we have not included the waiting time that is needed to implement the plane change. Remember, the plane change should always take place at the ascending or descending node, right? So here I have a waiting time for plane change, and as you can imagine, this waiting time is more than the waiting time for method A. Why is that? See, in method A, we were waiting in the parking orbit, right? So in method A, we are waiting in this small orbit. Its period is much low, so the spacecraft moves much faster, so the waiting time is less. Suppose here's my insertion point. Okay, this dot is the insertion point, so I need to wait until I get here or here, right? This is the waiting. Okay, but in method B, I'm in this big orbit. This is O2 prime, right? So my line of notes is the same. I need to wait until I get here or here. So obviously it's a bigger orbit, the speeds are slower, it will take more time to get there, right? So there are many different permutations and combinations that you can do to minimize the wait time. You know, it's basically about it's a matter of where you begin the Hohmann transfer. But just keep in mind that this number is only for the Hohmann transfer, not the waiting time that's needed to implement the plane change. Okay. All right. So the moral of the story here is that delta VB for this objective is less than delta VA, and I may even say much less, because you're saving about 2.3 kilometers per second, which is pretty big in terms of propellant mass, right? So method B, it seems, should be used to transfer the spacecraft from launch to geostationary orbit. Okay.